All right. So today we are going to finish up section 7.2, and I already uploaded the exam module. So let me kind of click on that. Let me see if they'll let me put it in student view. I can share the screen, or if they'll let me. Give me one. Oop. Okay. All right, so I'm going to stop sharing this just for a second. See if they'll allow me to share. Probably not in student mode or student view. Da, da, da. Yep, they won't let me share it in student view. Unfortunately, here we go. Well, if you go to your Canvas homepage, the very first module is the Exam 1 module. And again, we haven't finished all the way up to 7.2 yet, so that's when you'll finish it. But as soon as we finish 7.2, it's everything from 6.1 to 7.2 is covered in that exam. And I would click on this like a little lockdown browser quiz. All that does is make sure that you have the proper lockdown browser before you take the exam. Or if you already have it on there, you don't have to worry about it. And you have any time between now and the 31st to take it. So you don't have a rush, but I wouldn't wait till the very last day. The way Canvas has been acting up, I wouldn't trust it not to act up on exactly the 31st. All right, so let me go ahead and go full screen. There we go. All right, but today we're going to finish 7.2, and then after that, I'll let you out early because this way, if you have any questions, you can ask like the last portion of class, or if you want to just go over the stuff that's going to be on the test, you can do that. And then tomorrow we'll do a full course or the full class time. But usually just before the test, I give like 1.5 days you can concentrate on test material. Okay, so with this part of 7.2, we are looking for the guidelines for evaluating integrals involving secant and tangent. Last time we looked at like different exponents of sine and cosine and different combinations and how to approach those. With secant and tangent, let's say we know that when the exponent of secant is even and positive. Okay. So we knew when we did sine and cosine, if you had an odd exponent for either one of those, you'd factor out one of the sines or cosines, and then you replace sine, or sine squared with 1 minus cosine squared, cosine squared with 1 minus sine squared. This is kind of the same idea. But in this case, you're going to factor out the secant squared and convert the remaining tangents. So that means you're going to use your secant squared is equal to 1 plus tangent squared. Okay. And just like before, it just all comes from, oh, not secant squared. Sine squared plus cosine squared is equal to 1. You divide every term by cosine squared. You know, cosine squared divided by cosine squared is 1. So that gives us tangent squared, sine squared divided by cosine squared, plus 1 is equal to 1 divided by cosine squared, which is secant squared. So that's just where this comes from. If it's been a while since you've seen it. So all this is saying is that if you start off with an integral of secant raised to the power of 2 times some number, some even secant exponent, times tangent to the nth power of x. Make that n a little clearer. Okay. Then whatever this is, first thing we're going to do is rewrite it as secant squared to the power of something. To the power of that exponent k. So if you had secant to the 6th power, you'd have secant squared, and that raised to the 3rd power. So inside of here will always just be a secant squared. And it's still times tangent of x to the nth power. So you're going to take one of these secant squared, and you're going to factor it out. So that's secant squared. If that's to the power of k, you're going to make that to the power of k minus 1. You're going to factor one of those out. Then this is just going to become tangent to the nth power times secant squared. Just take one of those and factor right in there. Then the secant squared inside the bracket, that's the one you're going to replace with 1 plus tangent squared. So times the nth power of tangent times secant squared of x. And doing that should put it in the form to where you can actually use substitution. All right, so let's say, for example, what if we wanted to evaluate the integral of secant of 3x to the 4th power times tangent of 3x to the 3rd power with respect to x. Okay. So we can see here that our secant term is raised to the exponent that's even and positive. So that means we're going to take that secant of 3x to the 4th power and we're going to rewrite that as secant squared of x, of 3x. Squared. All that does is take our original integral and we just rewrite it as secant squared of 3x squared times tangent to the 3rd power of 3x with respect to x. So we take one of those secant squared and factor it out. So that means this secant squared of 3x to the 2nd power just becomes secant squared of 3x to the 1st power, or just secant squared of 3x. times tangent to the third power, 3x, times secant squared of 3x with respect to x. Now remember, this was the one that was originally in the brackets. So the one that was originally in the brackets, that's the one we're going to convert to 1 plus tangent squared. So now that just becomes 1 plus tangent squared, 3x, times tangent to the third power of 3x, times secant squared of 3x with respect to x. Kind of cover that up here. Now, once you do that, now you can start your u substitution. You have everything in place. Okay? So we're going to let u equal tangent of 3x. So we know tangent of x is just secant squared. Tangent of 3x, which is our derivative of u, is 3 times secant squared of 3x with respect to x. So if we divide both sides by 3, that gives us du divided by 3 is equal to secant squared of 3x dx. So if we did everything correctly, this portion right here is just 1 plus u squared. This tangent to the third power, that's just u to the third power. And that secant squared of 3x with respect to x, that part just becomes our du divided by 3. Or you can say 1/3 du. Either way works. Make that a little neater. There we go. So if we rewrite it in terms of u, that 1/3, we can just factor that right out to the front. So the integral of 1 plus u squared times u to the third power du. And make that a little smaller. So now all we have to do is distribute that u to the third power. So that gives us 1/3 times the integral of u to the third power plus u to the fifth power with respect to u. And from there, we just go ahead and integrate each term. That's 1/3 times the integral of u to the third power, which is u to the fourth power over 4, plus the integral of u to the fifth power, u to the sixth power over 6, plus c. So go ahead and distribute that 1/3. That gives us 1/12 u to the fourth power plus 1/18 u to the sixth power plus c. A little. Okay. Once you do that, the only thing left is just to replace your u, which is tangent of 3x. So that becomes 1/12 tangent to the fourth power of 3x plus 1/18 tangent to the sixth power of 3x plus c. All right. Any questions on that one? All right. Let's do one more example. Anyone still writing? Okay. Okay, so let's say if we wanted to evaluate integral tangent to the sixth power of x times secant to the fourth power of x with respect to x. I probably should have picked one with a different exponent. Didn't even realize I had secant to the fourth twice. Make a note of that. So again, if you look right at our secant, and we know this is an even and positive exponent. We know that we're going to take our secant to the fourth power, and we're just going to rewrite that as secant squared to the second power. Just for future, let's say if you had secant to the sixth power, that's just going to be secant squared third power. So if you add secant to the 10th power, that's just going to be secant squared to the 5th power. 2 times 3 gives us 6. 2 times 5 gives us 10, and etc. So that means take our integral of tangent of x to the 6th power, and we can put a little square around that. That's secant to the 4th. We're just going to rewrite that as secant squared with respect to it. And I really wish I would have noticed that I used secant to the 4th twice. Didn't pay attention to that. Okay. So again, here we're just going to factor out one of those secant squared. So the whole point is to get a secant squared of x dx, or secant squared of whatever with respect to u. Take the integral of tangent to the 6th power times secant squared of x. One of those we're going to factor out. That secant squared that we factored out just ends up next to the dx. And the one that was in the bracket, remember, you're going to convert it to tangent squared plus 1. Or 1 plus tangent squared, doesn't matter. So we have the integral of tangent to the 6th power of x times 1 plus tangent squared times secant squared of x with respect to x. All right, so once we have it in that form, that's when we can let our u equal our tangent of x. Our derivative of u is equal to the derivative of tangent, which is secant squared with respect to x. And there's no coefficient, so we don't have to worry about dividing both sides by anything. Okay, so this tangent to the 6th power, that just becomes u to the 6th power. This 1 plus tangent squared, that becomes 1 plus u squared. This secant squared of x with respect to x, that just becomes our du. We rewrite it in terms of u. That's the integral of u to the sixth power times 1 plus u squared du. Now, then from there, all you have to do is distribute your u to the sixth power. So we have the integral of u to the sixth power plus u to the eighth power with respect to u. Okay, so go ahead and integrate each term. The integral of u to the sixth power is u to the seventh power over 7, or 1/7 times u to the seventh power, plus the integral of u to the eighth power is u to the ninth power over 9, or 1/9 u to the ninth power, plus c. So once we get to that point, the only thing left is to replace our u, which is equal to x. So that gives us 1/7 times tangent of x to the seventh power plus 1/9 times tangent of x to the ninth power plus c. All right. Any questions on that one? Right. Okay. Look like everyone's done writing. Okay. So we know what to do when the exponent of secant is even and positive. But what if we have that secant and tangent combination and we know the exponent of tangent is odd and odd and positive? It's going to factor out a secant times tangent. And convert the remaining tangent squared to tangent squared of x equals secant squared of x minus 1. Okay. So the process is similar to what we did for the even exponent of secant. Okay, so kind of the general idea of the steps. Let's say if you have the integral of secant of x, let's say that's raised to the power of some exponent m. And tangent of x, if that's to an odd exponent, so let's say that's to the exponent of 2 times k plus 1. That make that a little neater. 2 times some whole number k plus 1 will be an odd number with respect to it. Okay? So we're going to factor out a secant x and a tangent x. Factor out secant of x times tangent of x. So that means if we have secant x to the power of some number m, that's going to become m minus 1. Secant to the power of m minus 1 of x. Same thing here. We have an odd number of tangents. We're going to take one of them and factor it out. So that's times tangent to the power of some even number now, 2 times k. The ones that we factored out, we'll just put them right in. So that secant we factored out, we'll just put it right there. And that tangent that we factored out, we'll just put it right there. So this even tangent, remember, you can rewrite this as tangent squared of x to the power of k. Same way we do with secant. So once you get there, now you're just going to replace that tangent squared with secant squared minus 1. Give that a little more space. That means we'll end up with an integral in the form of the integral of secant to the power of m minus 1 instead of tangent squared to the power of x. That's going to become secant squared minus 1. I mean, to the power of k, that is. Tangent squared to the power of k. So that becomes secant squared minus 1 to the power of k. Times secant times tangent of x. got my secant squared of x minus 1. The only difference is this time we're going to make our secant equal u. All right. So let's say, for example, we wanted to evaluate the integral of secant to the fifth power of x times tangent of x with respect to x. You can see that this tangent is raised to the first power. So we know it's odd and positive. Underline the wrong. Oh, nope, that's the right one. Because we're converting the secant. Okay, so that means we're going to factor out a secant from this one. I'm just going to rewrite it. So instead of secant to the fifth power, I'm going to rewrite it as the integral of secant to the fourth power times secant. You'll have that times tangent there. So times tangent of x with respect to x. Okay. So what if we let u equals secant of x? And we know the derivative of secant is secant times tangent dx. I should have made that a little bit more so I had room to write under here. Okay, so this secant to the fourth power becomes u to the fourth power. This secant times tangent with respect to x, that becomes our du. So it just becomes the integral of u to the fourth power du. So the integral of u to the fourth power with respect to u is just u to the fifth power over 5 plus Then from there, all we have to do is replace our u. So that becomes 1/5. And u to the fifth power is just secant to the fifth power. So secant of x to the fifth power plus c. All right. Any questions on that one? All right. Looks like everyone's done writing. Okay, so what if we wanted to evaluate the integral of secant of x to the third power times tangent of x to the fifth power with respect to x? Okay, we can see that our tangent exponent is odd and positive. Okay, so that means the first thing we're going to do is factor out the secant. Didn't need to write out the whole secant. But remember, we want it to be secant x times tangent x dx. So we want to factor out a secant and a tangent. Now, on the last one, it was only a tangent of x, so we couldn't factor out a tangent because we already had a tangent there. Okay, so since it's only tangent to the first power, that was the one we used for our secant times tangent. This one, we have a couple of secants, so we can factor out a couple of secants, a couple of tangents, so we can factor out a tangent. So that's just going to become integral of secant squared. Going to take one out of there. Times tangent to the fourth power of x. And the secant and tangent that we factored out just go right at the end. Remember this tangent to the fourth, we can rewrite that as tangent squared squared. Okay. So we're going to replace that tangent squared with secant squared minus 1. marks around that one too. So we have the integral of secant squared. And instead of tangent squared, I have secant squared minus 1 squared. So secant squared of x minus 1 squared times secant times tangent with respect to x. So secant of x times tangent of x with respect to x. All right, so I'm going to give it a little bit of room because I'm going to mark over there. We're going to let u equals secant of x. Means the derivative of u is equal to secant of x times tangent of x with respect to x. That means this secant squared just becomes u squared. This secant squared minus 1 squared, that just becomes u minus 1 squared, or u squared minus 1 squared. And this secant times tangent with respect to x, that just becomes our du. So if we rewrite that in terms of u, that just gives us the integral of u squared times u squared minus 1 squared with respect to u. With this one, we can't just distribute the u squared because we have u squared minus 1 squared. So we have to convert that squared minus 1 squared. You know that's just u squared minus 1 times u squared minus 1. FOIL method, that's just u to the 4th power. Our outer is negative u squared. Our inner is negative u squared. So it's minus 2 u squared plus 1. So that gives us the integral of u squared times u to the 4th power minus 2u squared plus 1 with respect to u. Now we can distribute. Once we got rid of that u minus 1, u squared minus 1 squared exponent, that gives us the integral of u squared times u to the 4th, which is u to the 6th power. U squared times negative 2u squared is negative u to the 4th power. And u squared times 1 is just u squared. with respect to you. Now, once you get there, we just have to integrate each term. So the integral of u to the 6th power is u to the 7th power over 7, or 1 over 7 u to the 7th, minus 2 times the integral of u to the 4th power, which is u to the 5th power over 5, or 1/5 u to the 5th power, plus the integral of u squared is u to the 3rd power over 3, or just 1/3 u to the 3rd power, plus c. Okay, and other than multiplying this -2 and 1/5, the only other thing we have to do here is just replace u. Our u is secant of x, so that gives us 1/7 times secant of x to the 7th power minus 2/5 times secant of x to the 5th power plus 1/3 secant of x to the 3rd power plus c. All right. Any questions on that one? Excuse me. Okay, looks like everyone's done writing. So let's say if you're going to integrate and there's no secant factor. And we know that the power of tangent is even and positive. Then you're just going to convert one of those tangents squared to 1 to secant squared minus 1. Secant squared of x minus 1. So what if we wanted to evaluate the integral from 0 to pi over 4 of tangent of x to the 4th power with respect to x? So I did not notice how many tangent of x to the 4th powers I had. I was just randomly grabbing examples. So if you don't have a secant you can factor out, first thing we're going to do is factor out a tangent squared. So that means we have the integral from 0 to pi over 4, our tangent squared of x, times the tangent square that we factored out, with respect to x. There, we're just going to replace that tangent squared with secant squared minus 1. So that gives us the integral from 0 to pi over 4, secant squared of x minus 1 times tangent squared of x. And there, we're just going to distribute that tangent squared. So the integral from u to pi over 4, we have secant squared times tangent squared minus tangent squared. So now we can split them up to two separate integrals. The integral from 0 to pi over 4 of secant squared of x times tangent squared of x with respect to x minus the integral from 0 to pi over 4 of tangent squared of x with respect to x. We could actually switch these two around if you wanted to. You don't have to, but you can. Because for this one, we're going to let u equal tangent of x. which means our derivative of u is equal to secant squared of x with respect to x. For this one, you can see that tangent has an even and positive exponent. And we could have done the same method over here if we wanted to, but this one kind of worked out so where it was straight u substitution. So this one, we have an even and positive exponent, which means we're going to replace tangent squared with secant squared minus 1. So this first term integral from 0 to pi over 4. If you switch these around, you'd have tangent squared times secant squared dx or u squared du minus the integral from 0 to pi over 4. We're going to replace tangent squared with secant squared minus 1. This one, we're going to go ahead and distribute that integral again. And you can integrate this one here, or you can wait. I'm just waiting. Integrate them all at the same time. We have the integral from 0 to pi over 4, so u squared du, minus the integral from 0, that looks a lot like a 6. This should not be a 6. There we go. To pi over 4 of secant squared of x dx, because we haven't converted that yet, minus the integral from 0 pi over 4 of 1 dx Actually, with these two, you could have kept them like this together, but separating them is no big deal. And these two are still with respect to x, so you don't have to convert them. Let me write it on the next page. So I'm trying to squeeze everything here. Oh, and glad I caught this error. You have the negative integral and negative 1, so this should be plus 1. Anyone still writing? All right. And so if we take the integral of u squared, that's u to the third power over 3, where you say 1/3 u to the third power. Remember, that's from x equals 0 to x equals pi over 4. So we have to either replace the u with our tangent of x, or we have to take u of pi over 4 to u of 0. I just usually replace the u. It makes it easier. Minus the integral of secant squared. The integral of secant squared is tangent of x. Tangent of x. Actually, we just do both of those together. Plus the integral of 1, which is just x. They're already separated. 0 to pi over 4 plus the integral of 1 is just x. So that's x from 0 to pi over 4. So again, all we have to do now is just replace that with tangent of x. And I'll just say tangent of x to the third power. Instead of having the 3 in between there. 0 to pi over 4 minus tangent of x from 0 to pi over 4 plus x from 0 to pi over 4. And again, I'm doing it the very long for the sake of explanation. I'm pretty sure a lot of you are doing it a lot faster than this. Now that we converted that from being a function of u to a function of x, and all of these from 0 to pi over 4, just for the sake of space, I'm going to put them all together instead of doing them all separately. So 1/3 tangent of x to the third power minus tangent of x plus x from 0 to power 4. And from there, we just apply the fundamental theorem. So move this out of the way. So we plug in our upper bound. So that's 1/3 times tangent of pi over 4 to the third power minus tangent of pi over 4 plus pi over 4 minus, we go ahead and plug in our lower bound. That's 1/3. Honestly, all of these will end up being 0, but we'll write them in anyway. Tangent of 0 to the third power minus tangent of 0 plus 0. And give that. Let's get that bracket in there. There we go. That's good enough. Again, this is just 0, 0, and 0. So those can just disappear. Tangent of pi over 4 is equal to 1. So this is just 1 to the third power. Oops. So 1 to the third power times 1/3 is just 1/3. minus 1 plus power of 4. Now, if they want the exact answer, once you get 1/3 minus 3 over 3, that's negative 2 over 3. It just becomes power of 4 minus 2 over 3. Or if you plug that into your calculator, you should get approximately 0.119. Like I said, depending on what form they want the answer. Any questions on that one? All right. Okay. Now, in this case, what if you come across one where your angles are different? If that's the case, you're going to use the reduction formulas. Or also known as the product identity. These should look familiar from trig, but if you don't remember them, don't worry. It's one of those things where it's really easy to not remember these if you don't use them all the time. So what if we have sine of A times sine of B? That's equal to 1/2 times cosine of A minus B minus 1/2 times cosine of A plus B. But what if you have a sine cosine with different angles? You have sine of A times cosine of B. That's equal to 1/2 times sine of A minus B plus 1/2 sine of A plus B. Or if you have cosine of A times cosine of B, and make that B a little neater. That's equal to 1/2 times cosine of A minus B plus 1/2 cosine of a plus b, which is really, really close to sine a times sine of b, but different sign. Now I'll do the next example on a different sheet. I was trying to figure if I had enough room to solve it on this one. All right, anyone still writing? All right. So let's say, for example, if we wanted to evaluate the integral of sine of 7x times cosine of 2x with respect to x. So this is a sine-cosine combination. So we're going to look at integral sine of a times cosine of b. We know that's equal to 1/2 times the integral sine of a minus b with respect to x, plus 1/2 times the integral sine of a plus b with respect to x. Right, so all we did was pick our combination and integrate both sides, which was this one here. Or integrate each term. Easier way to think about it. So if we have the integral sine of 7x times cosine of 2x with respect to x, this is our a, and this is our b. And that's going to equal 1/2 times the integral of sine of a minus b. And I'll put it underneath just to avoid running out of room. So that's 1/2 times the integral sine of 7x minus 2x. With respect to x, plus 1/2 times the integral of 7x plus 2x. With respect to x. All we did was plug in our a and b. So that gives us 1/2 times the integral of sine of 5x with respect to x, plus 1/2 times the integral sine of 9x with respect to x. Okay, so let's find the integral of sine of 5x. I'll just solve that right over here. Put it on the right. I'll put it on the right side. This way I can put it right up underneath the actual integral. There we go. Now put it over here. The integral of sine of 5x, we let u equal 5x. And the derivative of u is 5 dx. Divide both sides by 5. D over 5 is equal to dx. This integral ends up being the integral. Give that a little bit of room because we're going to go ahead and factor that 1/5 out right from the beginning. Of sine of u times dx, which is d over 5. Again, we're going to factor out that 1/5 and just put our du right there. So we know the integral of sine is negative cosine. That gives us 1/5 times negative cosine of u plus c. And once we replace our u, move that down a little bit, that ends up being negative 1/5 times cosine of 5x plus c. Okay. So that gives us 1/2 times the integral of sine of 5x, which is negative 1/5 cosine of 5x, plus 1/2, and using the same process for this one, getting negative 1/9. Negative 1/9 times cosine of 9x plus c. So go ahead and multiply those two factors. You have negative 1/10 times cosine of 5x minus 1/8 times cosine of 9x plus c. So a lot of times, problems like that that look really crazy, you just have to kind of search for the right trig formula that you probably just forgot. It's probably covered it one time, but like I said, if you don't use it, it'll just seep right to the back of the mind. Any questions on that one? All right. So that is it for 7.2. So we do have the exam posted, well, the exam not posted. So I'm going to go ahead and stop there. So if anyone has any questions about anything that's on exam one, feel free to hang back and ask. I'm more than happy to help. If not, we'll see you tomorrow when we will start on 7.3. All right, you too. You too. See you next.
Just like related.
Sure.
I did like a little bit busy, so then like finished all of it too. So at least fine if I finish them in the next 2 days. Fine. Because see if there's no due date.
Actually, I just added to do that because we had people arriving late last week.
Sounds good.
Yep. So double check up. The chapter 6 are all due on the 29th, and the chapter 7:1 and 7:2 are due on the 30th. So basically, we had people still
Yeah.
coming in, so I was like, that's why I didn't put a due date. But once they're officially enrolled, I was like, okay, now I can put a due date.
Sounds good.
All right.
Something like that.
You
That's the
too.
same question.
You too. Yep, for the exam review, you can go over your notes and homework and all of that, or you can just go for the review that I posted. With the review, what it does is it kind of takes it to where you don't have to go over everything. It just focuses on kind of just the area that's going to be on the test. The review gives you a more detailed area of focus. All right, so what I let me see, we should be able to ask. This is why. And what I'm doing is because Canvas is starting to really annoy me with all these glitches, is that I created a YouTube page specifically for my Calc 1 and Calc 2 this semester. So what I'm going to do is upload those videos to YouTube, and then this way I can just get the YouTube link in Canvas, and you don't have to worry about it expiring or none of that stuff. So it'll be there. All right, so give me, like I said, should be by tonight because I tried doing it here. They wouldn't let me download the video, so I'll have to go home. And I thought maybe I could do it here and save some of my memory space, but they won't let me do it here. So I have to just download them to my external hard drive, and I can upload them, and hopefully all that works out. Yes, exam one is due on the 30th, but I gave everyone a 1 day grace period, so it's due on Sunday the 31st at midnight. Yep. Chapter 6, 7:1 and 7:2. Hey, thank you, Donovan. You have a great day too.